秋北海道とやらを行きます。鋼鉄を
that's the contribution from the Atlas 9 series. Turn on the right. So in conclusion, so since what normal basis? Thanks. So since I guess we take the constant function, it's normalized to be a probability measure, and since the ordinary uniform measure vanishes for Eisenstein. This is a standard reaction that suffices to show for steps of psi, meaning psi with a cusp over Eisenstein, that if psi is bounded by negative delta, will be allowed the implied constant dependent upon psi. But maybe, for missing a small detail, we should require the dependence to be reasonable as t varies. So, polynomial splice is probably measurable. Yeah, that's not like you do a basis. Yeah. Sorry. Yeah, there is no positive number. Exactly, yeah. Delta, the convention is just a very small, very existent delta. Maybe I should have emphasized it. It's a little too in the theorem, so I'll explain why in a second. So, okay, I have the proof is actually, the structure of the proof is kind of surprising and interesting, so. Yeah, so there's this annoyance that, so I was thinking to split the levels in this talk because of basically a lack of vocabulary on the part of the number theorists to properly formulate in a concise manner which vectors one should choose in other aspects that are not square free. So, group forms we can of course refer to in a public talk without having to define, but kind of group forms are not the right vector to choose for powerful aspects. So maybe the way to kind of reconcile the two questions is the shape does not follow the local means by say choosing the wrong vectors. So it's the first one that actually gives us a second best estimate. Okay, that's the had a paper actually recently where I gave a candidate vector that fixes this issue in the depth aspect, so we're going to do a micro-localist category that addresses this. I'm going to title the localist, but the key question is the next question. Okay, so I want to show this estimate that I've got here, on the side of the system point. And there's a little formula for this, so it's a formula through Watson in 2002, building on work of Harris and Kugla in 91, and then kind of the nest with a little aspect on myself in 2011, and many more people at GPU will find this kind of stuff quite a bit, which says that conditions are written down on the right hand side. This split period is given by Cohen function. So this is the period where the polar product, which will do us no service to define, divided by n over the conductor. And I'll put the same over the conductor exponent a little of 1. The meaning of little of 1 is something that tends to 0 for psi first, and let's say the parameters of phi tending to infinity. The L function is known in this case to be non-negative value. So in fact, I guess this one includes it, but yeah. Just for the sake of expediency, I'll introduce the definition. I'll call this right-hand side L over C to the quarter plus L over 1. Okay. So this also is like a very standard direction. Here I have uses to the Cohen estimate of star, which says that L over C to the quarter is bounded by the same C raised to the negative delta times what's also polynomial dependence on the conductor side. Something like that. So this is for some delta greater than 0, maybe A greater than 1. And so, I mean, those of you who know this is a subject density problem, so we're going to address this by proving a subject bound in this case. It's worth also noting that in this case, since number I defined to be C up here happens to be roughly of size p to the fourth. So these are fixed values of psi. So saving a power of C is the same as saving a power of B.
左左右どっちが左
I guess I'll leave the theorem statement in the middle for now. Now let's do kind of a very
東京に向かいます
So I call this estimate asterisk. And then almost your asterisk. Let's divide asterisk into two cases. Let's call one case case A and one case case B. Where A is the case of asterisk in which we get a fixed function of size, not just time series. Let's call this here B. Case where psi is decimal. So if we treat both of those, then we have clear. So the structure has a way kind of interesting form. So on the one hand, go in some way. This also explains the division of the critical theorem. So here at M, I'll state an assertion that holds. And then theorem N, the credits and names kind of an obvious sense there. So you expect to say that B holds. Speaking more honest, what it actually shows is that A implies B. And then the two of them together, there's a problem up there on N. So this is the machine, and this is nice. So I'll spend the rest of the talk kind of explaining the proof of what I call theorem N here, like why in the world there should be any implication between two sets of the shape. But I don't think there's any pre-existing intuition or kind of model result on which to base an application like this. I mean, for most purposes, the contributions of these two parts of the spectrum don't really see each other. But I should say, I mean, the preprint is still being finalized, so we should, well, I mean, it is being finalized. We talked about it, mentioning that quite a bit while he was here. This preprint is at least available and submitted, so that's what I'll talk about for the remainder of the lecture. And maybe it's worth noting that in this theorem, what I call theorem A, the case with size Eisenstein is a factorization of the L function into order factors of the greatness 3. So that doesn't have the addresses. And it seems pretty clear to take just that fact the higher degree L function that comes up in part B. That's an interesting question. So at present, my result seems to require square free level without further work. So it requires something really non-trivial to any other aspect. If maybe ask me at the end of the talk, again, I'll say it in one, which is result is not good. I can imagine square free level would be no issue. But there's a very, very bizarre restriction in the method at the moment to essentially ground level. So let's talk about the proof of theorem N. So let's remember what we started with. We went about L over C to the quarter So when I got into this problem, some work I've been doing over the past 7 or so years, where I've been studying expressions that involve here in phi, using something called the Shimizu finger lift. It basically expresses phi of z1 times phi of z2. As an integral, but I don't have time to explain in detail, but with the integral, let's say phi of w, and then some complicated theta function, depending on all three variables. In case everything plugs in a sufficiently precise form of this identity into this inner product, one gets an expression of the following shape. So I'll define everything on the export. So I'll call it phi theta sharp h sharp. Split it. So the first step in the proof is we're going to study this ratio of all functions, or equivalently this period, by means of this particular integral representation. Now, I mentioned in fact, so actually in the article, there's a lemma of Yan Chu, that he proved on some other results on static copper kernels, together with some local calculations. That worked out to kind of give this error directly. Anyway, I mean, his proof actually goes through the same set of indications. So the first step is to kind of linearize the problem with respect to phi using the Shimizu lift, and then zoom in on that motor item. So H sharp is a half an hour waveform on gamma naught of 4p. Just worth emphasizing that all these h's depend upon psi. That's what enters into the discussion. And there's a useful fact, which is that it turns out that H sharp has the same LT norm as H. Which is not entirely obvious, but it's useful. So this inner product I'm putting down here, all three of the forms are effectively unit vectors. And the fact that you can actually position yourself, you can find an integral representation where all three of them are unit vectors, and they satisfy some other conditions like one of them is unramified. This is kind of specific to this work level aspect. And represent this as one of the abstractions to kind of generalize on this method in the trigger. Okay, so we arrived at this problem of bounding this inner product by a small power of p to the negative delta. So now there's a technique called the amplification method. So, two various people, Vanya Sarnak, Friedman Radonjic, Venkatesh, Vishal Venkatesh, in the 90s and early 2000s. So what I call star stack, hologram, there's a lot of third star. But triple solid maybe assertion that we take multiply by theta sharp, and we take the L2 norm, and we can produce an asymptotic formula for this L2 norm. Plus some very small error. And I'll say informally with a bit of room. To actually prove triple star. Before I do that, I want to say just a couple more words to kind of give you an indication of why it's plausible that triple star should be sufficient. So what we really need is, so we use half an integral F operators. So for small L, that are squares, maybe L is of size, maybe alpha, where alpha is small and positive. So what we really want is the F operator. P theta sharp. P theta sharp. And we get 1 over the degree of the Heck operator, which is something like L. Times the corresponding inner products on the radiant side. Just that is like small p, and maybe 2 over the L in L. So p to the negative delta. there is that when you write down the proof of triple star, it's going to be very obvious with every step that the proof more generally extends to give whatever element or blackboard with this number here. And so the application method is all about taking a statement like this and using it to buy a little bit in the main turn. So the idea is that if star fails, then Cauchy-Schwarz identity, B, theta sharp, H sharp, so it's being bounded by, say, B theta sharp squared. So it's nearly sharp. So more speaking, B theta sharp is kind of nearly a multiple of H sharp. Which can be seen in contradicts. Why we're in here. Say triple star, so it's triple. So typically TL H sharp is something like, well, lambda B of H sharp 3L is typically about 1 times H sharp. But you can check that imply TL to B and to consider product, we'll do the same thing with H sharp. This side here is bounded by L to the 3/4. This side here is bounded by, say, L to the quarter plus 7 over 64. Which is in particular bounded by L to the 3/4 minus beta. So this is bounded by L to the 3/2 minus beta. You're going to write as 1/2 minus beta times degree TL, which is contrary to the asymptotic relation that I've written down here. The main question that I'll address in the last minutes of the talk is how do we actually establish triple star?
Curious.
So we're going to use the spectral theorem on page 1 as we said. you heard, the book created different square cancellation objective functions. Now we'll focus on a specific kind of objective function, which is grouping characters. The methods apply a bit more generally than that, so if people are interested in that, they can ask later. And the plan of the talk, so first of all, there'll be an introduction, and I'll talk about square root cancellation a bit and state some results. And the results will be of two kinds, so there'll be results in a sort of random model problem. So how does a typical objective function behave? And so in the second part of the talk, I'm going to say something about the ideas of proof in a random case. And the concept that we use results of random case to teach you things in some deterministic settings as well. So the third part of the talk is going to be just a little bit about proof ideas in the deterministic case.
すべては国道それたのが間違いだ。
So I guess you check at this point, is that visible at the back? Okay. Right. So let's start with a very straightforward problem, hopefully. So, we'll let R be a large line, because D and Q will be used in other things later. And X, somewhere between 1 and strictly less than R, say. And then I want to look at the sum of the group character chi over 1 less than X, and I'll square this and average on the character. So sum over all the characters chi with R, and R is pi, so there are R minus 1, of course. And I'd like to know how big this is. And of course we can do that. So we can expand X squared, so this is the sum over N1 N2 less than X, and I'll move this up to the inside. So pi of N1, pi of N2, conjugate. And now by probability, the only term that survive here are the ones with N1 that's the second moment, or the L2 norm square carrying sum. So I want to ask what happens to the L1. So the L1 norm, so 1 over R minus 1, sum over chi, carrying sum over the square. Right, so if you see this, I think there's precisely one thing you need to do, which is you can make the charts to get out the L2 norm. So, the charts.
Here, the right is here. Second moment, so that's square root of x. And what I want to know is that sharp or not? In order of magnitude. So if it's sharp, I'd like the lower bound to be L1 norm of the same size. If it's not sharp, I'd like to improve the upper bound. Right, so the questions about what I said so far. Okay, so what I'm going to do now is I'm going to hedge my bet a little bit. So first of all, I'm going to give some reasons why you might think that should be sharp, and then I'm going to give some reasons why you might think it's not. And then I'll state some theorems. So my folder combining this with the L2 result that I called star somewhere there. So combine this with star gives a lower bound.
環状2号17号がありました。17号まで。チェックだよ。環状2号81。はい、環状2号がありました。
Okay, so it's a slight-based random function because it's built from these slight-based random variables. It's not predictive because you can see that the value n is built multiplicatively for the values at programs. And actually, it's totally multiplicative, just like a characteristic.
環状2号新横浜まで行きます。
And in this setting, there's a conjecture of Helson from 2010, which is that if you look at the L1 norm, so here the L1 norm is just this expectation of the absolute value, this should be a little over the square root x. to go back to proving this, no upper bounds are going to affect square root x. There were some lower bounds, so the lower bounds of Helson himself, following from his work, and of Bondarenko and Sipe, and of myself and Bali and Lorenzo. And we showed that the expectation is at least as big as root x over log of x cubed, roughly. So if the conjecture is true, it's at least not very true. It can't be too much more than root x. But nothing was known about how to maybe prove this, but at least in this setting there was a conjecture that it should be the log square root x. Now I should say as well, why did Helson think this? Well, maybe. This is analogous to the following. I'll say one more reason why square root x isn't sharp. So what we've been doing here is we've been looking at problem 1 0 point. So we've taken the coefficients of the L function, the L function, and summed them up without any weights. And what we think about is what goes on the 1/2 line instead. So if we look at 1 over r minus 1, the sum over pi mod r, L 1/2 pi, the absolute value, which roughly speaking is the same as 1 over r minus 1, the sum over chi, mod r, the sum over n up to about r, chi of n over square root n. Okay, and now, so if what were going on was square root cancellation, then what you would expect is that this should be like the square root of the sum of the squares. So this should be like square root sum over n less than r, 1 over n, which is like square root log r. Okay, so square root cancellation suggests that's the answer, but that's not the answer. So actually, it's order log r to the power 1/4. And this is a result of looking at and it's underlying the lower bound the upper bound. Okay, so 1/2 is better than square root cancellation. And why is that? So why is it smaller? So this is because of the Euler product. Okay, so on the 1/2 line, even though the Euler product certainly doesn't converge anymore, it still has a big influence on the behavior of the L function, and the Euler product causes a sort of collapse. So you have a collapse in the size of the Euler product, which gives you this size. So you can think about the question, do we have square root x less than square root x for the L1 more back? So I'm asking a question, does the influence of the Euler product extend even out to the 0 point? So now I'll try to suspend using some symbols, right, and state some theorems. So theorem 1 is the random setting, so there, sine house, random function, and q between 0 and should be less than 1. Then if I take the here, this is a order magnitude, depending on q, x over square root of x. So this means it's at most some constant, depending on q times this, and it's at least some other constant, depending on q times this kind of thing. Right, so in particular, if you take q equals 1/2, then you get the L1 norm is like square root x over log of x to the 1/4. So the conjecture of Helson is correct. It is with log of square root x. So it's actually nothing. So now you can ask, so what does this mean for the character sum? So maybe this means that the character sum you set the square cancellation as well. Or maybe the random model is just failing to capture the arithmetic in the character sum problem properly. And we know that has to be the case to some extent because I already showed you that for a certain range of x, x's with r, essentially you do have square cancellation, and not square cancellation. But it turns out that's essentially the only case where you don't have that atmospheric cancellation. So this is 2, so let's R be large pi. And x will be 1 and R, 4. And the set L will be minimum of x and R of x. And then for any q bigger than 0 and greater than 1, we get upper bound. Actually, it doesn't matter. So R to q is less than depending on q x over the minimum of square root of L
横浜感情にも
and square root log R to the q. So provided that x tends to infinity and R over x tends to infinity, the denominator tends to infinity. So you have a less than square root of 2. So the second one becomes orthogonality, the same for the characters as for the random case. And what I'm saying is that the coefficient response for the second one of that is incorrect for the first one. And it's also incorrect for not as much Thank you. Other questions? Right. So I will say this about proofs. So proofs are quite complicated. So I'm not going to give even the detailed sketch of how to work. What I want to do instead is to just identify some of the issues that come up and how you might start to think about trying to solve them. So first of all, I'm only going to look so to idea, theme. So theme 1, I want to connect. So the undefined bound to the order product, which in this case is a random order product. So there's an order product times less than x, 1 minus f of b, EPS to the minus 1. Why do I want to do that? Well, actually, there are lots of reasons. So, first of all, it's the only clear part of the handling case, which here is the only case I'm interested in, where 2q isn't twice a natural number. Okay, if the exponent is twice a natural number, I can expand the square to do something. If the exponent isn't twice a natural number, I can't do that, so it's much less clear how to proceed. But if I can get down to the order product, then I'm much happier, because if I have an exponent 2q up here somewhere, it passes through the order product very nicely, so I just get exponent 2q here, and if I write this as an exponential, it just becomes a 2q as a coefficient exponential. So I'm much happier handling fractional powers, or not twice integer powers, with products and sums. So that's one reason. Another reason, so in the order product,
高速には乗ったんや
these terms, 1 minus f of p over pps, to the minus 1. the size, despite more conversion. So it requires a lot of work to see that it still governs the size, but heuristically that's why this is the size. If you pretend that this is like a random Euler product, this is the answer you get. If you pretend it's like a random sum, this is the answer you would get, which is wrong. Okay, other questions? Right. So I want to get the Euler product into play. How do I do it? So the obvious way is to use Coulomb. Okay, so everything is like 1 over 2 pi I, the integral line, and f is a finite, so I can have any qualitative abscissa of product 2. This won't work, so why not? So this is inefficient. Well, first of all, you have this 1 over s around, which isn't very good, because I'm probably going to end up putting some absolute values inside the integral at some point, and then I'll have something like integral 1 over mod s, which diverges logarithmically, and that's a disaster, because I'm trying to wing square root log x most, so if I lose a log, I'm done. Now you could fix this if you were happy with having a smoothly cut sum instead of a sharp cut-off, yeah, which you might be, but then there's a much worse problem. So first of all, that diverges logarithmically. Also, we would need to get cancellation from the oscillations of f of s times x to the it, which is generally very hard. Okay, so if I took c to be 1/2, which is the most natural choice, then I have an x to the 1/2 here, which would come out, and that would give me x to the q in the answer. I take the two q's on those. And then I direct from the integral, and what I'll be trying to show about the integral is not that it's smaller than a square parallel log, or even that it's bounded, I'll be trying to show it's actually small. So this is going to 0.5 log x. So to possibly do that, I need to show that there was lots of cancellation going on in these guys, which is very hard. So we're saying just a little bit about another way of proceeding. So instead, I'm going to let P of n be the largest factor of n. And what I can do is I can decompose my sum according to the size of P of n. So I split it up. The numbers n of P of n is at most x e to the minus k, and at least x e to the minus k plus 1. And then I can split up this sum, so every number here has at least one prime factor on this range, and a number which is bigger. So I can split these numbers up into the piece which has all of its prime factors on this range, and the piece which has prime factors smaller than this. And since n is multiplicative, when I do that, f will split up over these two sums. Okay, so this is the same thing as the sum over k bigger than 0, the sum over m less than x, such that if p divides m, then p is on that range. Yeah, strictly than 1. F of m, and then the other part, so the sum over n less than x over m. N is x e to the minus k plus 1, smooth. And the important thing to note here is that in this sum, we only have prime factors up to x e to the minus k plus 1. And in this sum, we only have prime factors that are bigger than x e to the minus k plus 1. And those things were chosen independently, so this is independent of this. Let's run through it. So how about that? Yeah. So if I hold that, if I have just some coefficients, some numbers, Cm, and we call this here I sub k, something more. So if Cm is just some numbers, and I look at what's the expectation of the sum over m with all of its prime factors in I sub k, of f of m Cm to the 2q. Well, my order, this is at most the expectation of the square of that sum, all to the power q. And then for the square, I can just expand that into reality, like usual. So this is the sum over m with all its prime factors in I of k, mod Cm squared, conditioning. If I call lots of lines here. So if I call this whole double sum here S sub k, inside there.
見かへんか。
If I look at the expectation of S sub k to the 2q, I can do the same thing, and I can get that this is at most the expectation sum with the prime factor condition. And then just treating the sums up there as deterministic coefficient. So the sum over n less than x over m, n is appropriately smooth. So n squared. Okay, so if you're not used to this, you just think, since I have this independence, I can freeze the things on the inside, then I can do Holger, like in the deterministic case, then I can re-randomize over the things on the inside. That's what happens. Or I can split the expectation up into the expectation of the inner thing, which is here, and the expectation of the outer sum, which goes away in the Holger application. Right, now, once you get to this point, you then do a few more steps, which I'll just list what they are. So now you can replace the sum over m by integral. Okay, when you do that, you pick up a weight to reflect the density of the second number of sum over there. Once you've done that, so you then have inside the bracket, you have the integral of the square of some sums at various points. So an integral of the square of some things looks a lot like the kind of thing you would hope to apply past that to something. And you can do that, so then you can apply a suitable form of Casimir. You do that, so on the physical space side you have the sum of f of n, on the frequency side you have the Dirichlet series of the So when you apply Casimir, what you finally get out, so of course I'm omitting lots of stuff here, so you get that this is roughly the same as x to the q times the expectation 1 over log x, short integral, so from -1/2 to 1/2, absolute value f of 1/2 plus it squared dt, all to the q. Remember that this is a finite product here. Okay, so if you see these kind of things before, maybe you can follow what happens in step by step. If you haven't, then you definitely don't follow what happens in steps by steps. The point I want to make is, why does this work? So why does this overcome the problem I was talking about over there? So there, I have this x to the it around, I need to capture some of this oscillation, I need to know how to do that. Here, I use Casimir, like Casimir, there's no oscillation. And of course now you have a mean square of something on one side, you have a mean square of something on the other side. So there's no oscillation that's been lost because there's never been oscillation in the first place. And you might worry that this whole step here is wasteful, but it's not, because in particular, if you look at the case where k is 0, which is one of the terms in the sum, then the sum over m is basically just the sum over primes, so just independent random variables on the primes. And we have a weighted sum of independent random variables, then this whole application is perfectly sharp, like Kitchen's airport, which goes along. So nothing has been wasted in this argument, and you've bypassed having to control any sort of oscillation, and the integral that you get, well actually it's not that, but something that you pretend is like that as the answer. Right, so now, to prove the theorem, what we want to show is that the expectation minus log x, integral of minus 1/2 to 1/2, f of 1/2 plus it squared dt, to the q is less than 1 over root log x. If q is stochastic 1. So down like 8 minutes left, something like that. Yep. Okay, so right, so I'll say a tiny bit about this, but I won't try and go into any details at all because I think it will just be too confusing to try and do that in time stand. And then after that I'll say a little bit about how you can transfer this to the deterministic setting. Okay, so a tiny remark about this. So if I take q equals 1, what happens? Well, if q equals 1, then the expectation and the integral can be small. So I get 5 log x, integral from minus 1/2 to 1/2, expectation f of 1/2 plus it squared dt. And this expectation is like log x in size, like second moments of z function or function. So this thing is all of 1.
幸福がありました。
Okay, as I said, this is log x.
12号。見た。
And now we're back to our discussion at the very start of the talk. So there are two ways that the expectation can be order 1. One way is it typically big in the brackets, the size of 1. Everyone's talking about how big on that. And another way is it usually usually a thing that is smaller than 1, but there are a few large points which will complete the expectation. And what we need to figure out is which of those is going on. If the answer were that it would typically be of size 1, then the answer on the right hand side would be 1. If the answer is that it's typically smaller than 1, then you'll have to get some skin. And the answer is that it's typically smaller than 1. Right. Maybe I can say one more thing about that to try to make you satisfy if you're interested. So to do this, what you need to do is you need to think about is it true that log x times this integral is roughly the same as 1 over log squared times the sum f of 1/2 plus I k over log x squared. So that is essentially true because this is like the Riemann sum for this integral, where I split up on a scale of 1 log x. But is it true that that's the case with the different things in the sum? So with f of 1/2 plus I k over log x being roughly independent of one another.
12ね。12です。
So there's a usual kind of heuristic that when you have another product like this, it sort of renews itself on a scale of 1 over log x. So when you move by more than 1 log x, you start seeing different behaviour. So there's a usual heuristic which I'm afraid I don't have time to explain if you haven't seen it before, but they should behave roughly like that thing with these things being sort of independent. But in this problem, the answer to this is no. So they don't behave roughly independently for the purposes of this problem. And this is ultimately where the 1 over root log x comes from. Okay, so this is where this comes from. We know there's this symmetry between x and other x. This is also why the one we brought up about, I showed you earlier, is true. If I have x being really close to 1 here, this sum is just about 1 terms, and everything is just controlled by this deterministic piece here. That's where they get this uniform half the pure plan. Right, so the last thing I'll say, so theorem 1, how we conditioned these primes f of b from b up to x e to the minus k. Right. So this is multiplied conditional. So for example, when k is 0, this is multiplied up to x to the y over e, power of x. So I can't really hope for anything like that. Push the calculus. Increase that conditional times up to x e to the minus k. Sharp result. There's one sub result, which is definitely square root cancellation, which for the moment I'd be happy with. So in this case, I don't have to condition all the primes up to there. I just condition on some of the primes and leave the others to be taken care of by holder. The holder argument always gives me like square root cancellation. And any primes I have left being put into holder, I hope to win something from. And this is how the argument works. So in the character sum case, just condition whatever the condition is. So just condition on the values pi and b, p up to about, let's say, log r over 3 quarters. Now I can do that because I have all of equal conditions, so that will maybe give me cut down the size of my space by something like that when I do the conditioning. So for that many conditions, I have r minus 1 characters. And this is much bigger than that number. So if I have much more characters than I have conditions, I'll still have a lot of characters left to each little box after my conditioning. And this will be enough to win something. Okay, so I think that will be a lot to do, so I'll stop. that would be the analog of what you get in the random case, except taking account of the symmetry between x and point x. So in that case, you save all to 1/4, okay, so the square consummation. Here you're saving a lot less. So I don't have to prove lower bound is going to determine the character subproblem. If you believe that by doing the lower bound in the random case, so if you believe that the character subproblem is like the random case apart from the symmetry of x over x down field. So it shouldn't make any difference. So I said, so as I said, there are two things that go wrong. One with the one rest weights. This would go away, this would wait. But there's also the problem. So it's essentially you want to win over one of the log x somewhere. So the size of fs that we're currently sort of expecting is like log x. So you want to win one of the log x to kill off most of the size. In Braun, you've never done that. You're just having fs right somewhere. The reason for that is because you have this oscillating x to the it, which gives you some extra saving, but it's very unclear how to calculate this extra saving. Okay, very much. We'll begin at 11 minutes. Thank you again. Nobody can compete with that. Anyway, right, so this work came out of an attempt to get a fresh look or try to understand better the inverse theorem for the Gauss norms over finite fields, for which we don't have a proof at the moment. We have a proof, but it's maybe, for a better understanding of it, maybe try to understand this theorem in more algebraic terms. So this is what I'm talking about. So this here is a model question. Okay, so suppose you have a group G. G is a group. Union. Incountable. And you have L is some vector space. Countable. Over some field F. Let me write K first. And you have a function rho from G to the endomorphism group of V. So these are homomorphisms from V to itself. And you're given this algebraic data that for any two elements, G and H and G, if you look at rho of G plus H minus rho of G minus rho of H, then this operator has rank that is bounded by some universal number R, great number R. Okay, so you're given that for any uniformly over the group G, for any two elements, you have an almost homomorphism. So if this were 0, this would be R would be 0. This would be a true homomorphism. So this is sort of an almost, in some terms, an almost homomorphism. And you want to answer the question. So the question is, can you find does there exist a question mark? Yeah, homomorphism, an honest to God homomorphism. Homomorphism. Chi, because I never remember how many n's, such that the rank rho is close to chi up to some bounded rank. Okay, so if I know that my function is an almost homomorphism in terms of rank, so the rank of rho of G plus H minus rho of G minus rho of H is smaller or equal than R, then can I find a homomorphism such that the difference between rho and chi is of bounded rank? Okay, depending so this number, well, obviously I have this infinite, so I want to find a finite R, depending on R. Okay, so here's like a baby question you can think of. Here's an example. Suppose your group G is just Z, and you're looking at this question, so you have this rho from G to end KV, and suppose this R is 1. So suppose you know that rho of G plus H minus rho of G minus rho of H, this rank of this thing is bounded by 1. Right? Suppose you know this, then it's not difficult to show. Then you can show, sort of follow this around, so you know that the kernel or the co-kernel is just a dimension 1. You can try to follow this around, and you can show that this R of R is smaller or equal than 2. So, okay, so you can do this. You can play around with this question and try to show this. But already I don't know how to do this if R is equal to 2. Okay, so. Yeah. Okay. I will describe an instance in a minute where we can solve this, but actually I'll give you kind of a framework. There's like a big stack of lots of problems that come up from formulating these type of problems, and kind of very basic ones we know nothing about. So for example, this one I can't answer. Here's what we can prove. So here's the theorem. If G is a V, which is a vector space over so infinite dimensional vector space over my field K, and K is a prime field. And characteristic
well, we can do it for greater or equal than 5, then the answer is yes. Then r of r is smaller than infinity. Yeah, so there is this function r, and of course you can also then ask questions whether how r depends on r, and I can't not going to be able to answer that. Yeah, but the point is that, well, this is a purely algebraic question, so I just ask the question, matrices or infinite dimensional matrices, and I know that this rank is, I'm just giving this condition on the rank, and the only way I know how to prove this is using analytic means. So I'll describe to you a proof of this theorem using analytic method.